Hi guys, so we are continuing with our set of problems for bitwise operations in Java. So the current problem that we are going to do is we have to find out the number of or the count of the set bits in a particular number. So we are given, suppose, an input of n is equal to 5. So what is the representation of 5 in bitwise format in Java? So it is represented in 32-bit format. So it would be 0 followed by 9 zeros and it would be 101. So as you can see that all of the values are 0 and there are 2 set bits, therefore we should be getting an output as 2. Now for the second input case, that is n is equal to 7. So for that, 0 followed by 28 zeros and 111. So there are 3 set bits, so we would be getting our output as 3. In case of n is equal to 30, 13 is can be taken as the sum of 8 and 4 and 1, right? So what should be the representation? It would be 1 1 0 1, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So 2 to the power 3 is 8, 2 to the power 2 is 4, 8 plus 4 is 12, and this is 1. So 8 plus 4, 12 plus 1 would give me 13, and the rest of the values would be 0, right? So the number of set bits in this particular representation of 13 is 3. So the output of the count of the set bits must be 3. Okay. So now let's try to solve for the naive solution. We would be doing 2 ways of solving this particular count of the set bits. So the first method would be the naive solution. Obviously, what would you guess as the naive solution? Till the value is greater than 0, I would have to right shift it by 1. If I keep on right shifting it by 1, and if we are checking whether each of the last bit is set or not, then we can keep the count of it. So what would the naive solution be? So let's write for the naive solution. So in case of naive solution, I would be shifting each of the values one by one to the right, and I would be performing an AND operation with 1. If I'm getting an output of 1, then I would be adding it to the count plus plus. Otherwise, I would be, if it is 0, I have to do nothing and I have to continue with the loop. Okay, so in the next iteration, it would become 0 dot 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 0 1 0. So again, so now it is 0, so I would not have to do anything. So the count is 1. In the next iteration, it would be 0 followed by zeros and 0 0 1. If I perform an AND operation again, it would increase my count value to 2, and on the last and performing the last right shift operation, I would be getting a value of 2, a value of 0. So I can just jump out of the loop whenever the value of this particular number is not greater than 0. If it is equal to 0, I can just skip it. I can skip the entire iteration. I can break out of the while loop. Okay, so let's now just go into our idea and try to code for it. Before that, let me just say you what must be the time complexity of this particular solution. This particular solution would have a time complexity of order of n, where suppose n is the number of bits used to represent a particular number, in number of bits to represent integer number, to represent integer. Okay, so order of n would be the number of bits to the order of the particular solution would be, or the algorithm would be, order of n, where n is the number of bits to represent the integer, or 32 in this case. It would vary with the system and the language that we are using, obviously. So let's now just go into our idea and start coding for this particular problem. So let's take a value of int n is equal to 5, and we would have to find out the number of set bits. So let's just initialize our count is equal to 0 while n is greater than 0. I would be continuing my loop. If it is less than or equal to 0, then there is no point of continuing with the 0. If I would have to provide a condition that the last bit of n and 1 is is greater than 0 or is not equal to 0, that is n and 1. So automatically I would be performing an AND operation only on the last bit. If it is 0, I would be getting a value of 0. If it is 1, I would be getting a value of 1. The rest of the bits would be 0 only. So I would check if n and 1 is not equal to 0, then I would perform the increase of the count operation, so count plus plus, and for the last thing I would have to perform n is equal to n double arrow 1. Double arrow means right shift 1, so I would be shifting it to the right position as we had seen in our logic before. So let's just print out the value of count and see what we are getting as our output here. So let's just run our code here, and we are getting 2 as our output here, which is expected from 5, as the number of set bits in 5 is 2. Let's check what our other test case was. Our other test case was 7. Let's just put n is equal to 7 here and run our code. We must get 3 as our output, as the number of set bits in 7 is 3, and we are getting 3 as our output. And for the last problem, that is 13 must also return 3. Let's run our code, and it is passing now, and it has completed its building, and we are getting 3 as our output again. So this is how you would be performing the count of the set bits in Java. So this was a solution that you performed in order of n. So is there any other solution where you can reduce the number of iterations? So let's just see what is the particular logic for that particular solution. Let me just clear this particular thing and this particular thing also. So now we are going to solve it with the help of an algorithm known as the Bryan-Kernigham's algorithm. So the algorithm is known as Bryan-Kernigham's algorithm. Let me first say you how is it better than the naive algorithm. Since before, a naive algorithm was taking an order of n, where n was the number of bits in a particular number. Bryan-Kernigham's algorithm does the particular work in order of k steps, where k is the number of count bits, number of set bits. So this is a good improvement over the initial algorithm. These small algorithms, when applied in a large test case, can solve lots of time and would help you not to get a time limit exceeded error. Okay, so how do we have to solve this particular problem? So you would know that what does minus 1 of a number, suppose a number is given such as 5, what would it affect on the what would 4 be? So what I'm exactly saying is that suppose I am taking n is equal to 40. The binary representation of 40 is given as 0 0 dot dot 0 1 0 1 0 0 0. So in case you have any doubt, it is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. So 2 to the power 5 gives me 32. 32 plus 8 would be giving me 40. 40 plus 1, yeah, that's it. So 32 plus 8 is 40. Let me remove these particular things that we have written right now, and let's just focus on what operations we will be doing. So if I perform, if I find out the binary representation of n minus 1, so it would be given as, it is equal to 39 obviously, and it would be given as 0 0 dot 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 0 1 0, and the values would be changing for this particular set from the first set bit, from the last set bit till the rest of the values. So for the rest of the values, it would be becoming zeros would be becoming 1, and this particular set bit would be becoming a unset bit. So if I perform an AND operation now, so if the value is greater than 0, I would be automatically getting that there is another set bit left. So we would be continuing in that case. So if I perform an AND operation now, the output that we would be getting is 0 0 0 1 0 0 0 0 0. Okay, so already the first set bit was nullified, and in the next iteration I would be performing an AND with this particular value. So this particular value is equal to 32, right? So n is equal to 32 for this particular operation, for this particular binary representation. I would be again performing an AND operation of it with n minus 1, that is 31. So n minus 1 is represented by 31, or it is equal to 0 0 followed by zeros and 0. The zeros will become 1 first, control, all of these would be 1 first, and this would become 0. Now if I perform an AND operation now, if I am getting that the value is non-zero, I would be increasing my count by 1. So initially the value was 0, I would be increasing my count by 1, count plus plus, and now also I would be increasing my count plus plus. Then if I perform an AND operation, I would be getting zeros. So since this is equal to 0, now we can exit our particular condition, right? So let's just start coding for this particular solution. So this is how Brian Cunningham's algorithm would work, and as you can see, it would only iterate for the number of set bits that we have, because in each iteration the set bit till the set bit, it is all of the values are set to 0, and we are performing on the basis of the next set bit. Okay, so let's just go into our idea console, and so let's take in our input as n is equal to 40. So as we had seen, it would be int n is equal to 40. So as we had seen that we had got 2 as an output, so before that let's keep a condition that we would be iterating in the loop till n is greater than 0. Otherwise there is no point of iterating on it, because we would not get a result anymore, and we would be reaching an infinite loop. So n is equal to what operation that did we do here exactly? We did the operation that we are performing an AND operation with the n minus 1 value. So I would be getting my new n. So n and n minus 1. So this is the operation that I am performing, and I would be also keeping a count variable that would be initialized to 0. So int count is equal to 0, and I would be increasing my count by 1. Okay, and let's just now run our code. And as you can see that we are getting 2 as an output, which is the number of set bits that are present in the number 40. Let's just check for another example. Suppose 13, and we must be getting 3. So let's run our code. It's compiling and it is successfully run, and we are getting 3 as an output. So we have successfully reduced the number of iterations that is required in order to count the number of set bits that are located in a particular binary representation of a particular number. So this is the Bryan-Kernigham's algorithm, and you must remember it in order to solve your problems in a much more faster manner. So thanks for watching this video, guys. I hope so you liked this, and if this was helpful for you, see you in the next one.